Hello and welcome to the video. I'm Jari Honkanen. I write about VHDL and FPGAs at hardwaredescriptions.com, and I wanted to make a video showing how to create reusable source code with VHDL using object-oriented design principles. What I'll be doing here is a first-order filter that is used to create some waveforms that are then streamed out of an FPGA. So I'll be synthesizing the code to FPGA and then plotting out the waveforms with MATLAB. So what I have open here is the VUnit script, which actually looks for any, it's a Python script that looks for any sources in these folders and runs any test benches it finds. So this streamlines the creation and running of test benches. The main entity that I have here is called LED blinker main, and it has a process inside which we create 4 LED blinkers. Then we initialize an uart which we use to receive data from an uart that is then transmitted or saved to the data from uart signal, and we create a time base from a counter that triggers this counter is ready, or if counter is ready statement at 100 kilohertz. We use 120 megahertz clock in the FPGA, thus this creates a 100 kilohertz time base. And at that 100 kilohertz we will actually transmit 16-bit words with uart. At this point we are simply looping in the data from uart Rx back to TX, so basically we are transmitting out the data that we get from uart. If we look at the code here, we can see that all of the functionality of the architectural body, or what is defined in this used in this architectural body, are inside these function and procedure calls. And if we look at, for example, the signals of the uart, we can see that they are actually custom record types, usually known as abstract data types, and these actually define all of the registers that are needed by the uart transmission and receiver, or when we use the uart transmission and receiver. So this is the basic way we create reusable code, because typically when we write any code inside the architectural body, there is no way to access it unless it is distinctly or specifically made accessible through the port of that entity. So since we now create all of the records, all of the registers in a record, and then we use or create the functionality with those registers using procedures and functions, we actually now have an access to the functionality outside of the entity to which they are created. Now the way we actually share the code is through the use of packages. So if we now create the source and filter, so we create the filter package. By the way, I use snippets, so I don't need to type in all of this basic boilerplate code here. So I have an object snippet which creates like a baseline object that does nothing, but we can actually create it and request action it, and it tells us when it is ready. So if we now create this filter package in which the filter object is defined, we can now see the idea here. So that first of all I have a record definition here. It holds all of the registers that is used by this object. Then I have a constant of that record type which we can use to initialize the record or initialize the object, and then all of the functionality that the object actually does is in the create object procedure, in this case create filter procedure, and then we access or request the functionality through the use of request object procedure, and then the object tells when it is ready, and we can catch this message with call to filter is ready function or object is ready function. Now, whenever we create anything, we should always first simulate it or create the test bench for it. And if we now create the test bench for the source and filters simulations and test bench filter.vhd, we will now create the test bench with which we can actually instantiate and simulate the filter that, like baseline filter that we just created, or the object that we created. So I have a snippet for unit test bench. This is going to be called db filter, and we are going to run it for 50 clock cycles. Also, we will save this file here, as well as this one. And at this point, we can actually already run this test bench. So we call to Python to run the unit run script, and what that does, it gives us this command line window here, which has the summary in which we can see that our test bench that we created is now found in this file, or found by the vunit. Now, next thing that we're going to do is we're going to open a new PowerShell with which we're going to open a GTK wave. So GTK wave vunit out test output db filter and VHDL and wave.ghv. We no longer luckily need this one. And now this is the empty test bench that we have just created. Now, as we open it, we can see actually don't need that. We only want to look at the simulation counter right now. Now, if we look at the counter, we can see that it runs from 0 to 49, at which point the simulation terminates. And that is because we defined the simulation to be for 50 clock cycles. Now, the next thing that we do is we will actually add library here. So library work, and here we will add the filter package. And we will then, first of all, make a signal of called filter, that is this filter record type, and we will init filter, which is the constant defined in the package, and we can actually now go ahead and create the filter. And then we will make an if statement that if simulation counter here is, for example, 5, then we will request filter called filter and end if. And by the way, I also use VHDL for syntax checking, and this VHDL compile let blink batch file simply compiles all of the packages in my project so that they can be used for syntax checking. Now we can already run this, or if we run this again, we can now see that we actually added this filter record type or filter object, and if we look at it, we can see that at 5th clock cycle, or actually 6th clock cycle, the filter is requested goes to true from false, and then at 6th clock cycle, 7th clock cycle, the filter is done. Now we can actually put the same thing here in the FPGA code, or the code that is synthesized to FPGA. So if we put here the filter package, and then we add the signal filter, which is filter record, and we initialize the filter. We can then add the create filter procedure call here. So create filter, and at 100 kilohertz we will actually request the filter, and we will change the code so that if filter is ready, then we will actually transmit the 16-bit word with uart and if. Now this can actually be synthesized and it will work just fine. The synthesis takes a few minutes, so we will go ahead and let it run for a while. Now at this point, the next thing to do is we will actually create or start typing in the filter in this procedure. Now first of all, what we need is we need to add the filter or the signal that we will filter into the request filter here. So we will put here filter input, that is an integer, and actually we will then also add it to the request filter here. I think we made a typo, so like this. Now it should say that there is an issue here because I made that, and in here we put in because it is in. So the declaration and implementation of the request filter procedure now has the filter input. And since we also need some sort of an output from the filter, we will create a function called getFilterOutput, which will get in this filter object. That is, of course, a filter record type. And it will return an integer. Now as of now, we will just return, let's say, 44252, because that is a nice big rocking number. If we go to the TP filter, we actually need to compile the packages. It will now say that our filter input actually requires some value, so we will put here 10,000, for example. Doesn't actually matter right now. And already we can run this. It shouldn't do anything different than it did before. It just returns true as before. Now we will add a new signal in the test bench called filter output. Let's put it output from filter, which is an integer that is defined as 0 or initialized to 0, and this will now be used to capture. So if filter is ready, then output for filter, then we will actually output from filter is get filter output filter and if, and we will also correct this because this needs to be just filter. No declaration for, okay, we forgot to declare this get filter output here, so we will do that now. So we will just add the get filter output to the declarative into the declarative region of the filter package. Now, as we actually compile our packages again and check for syntax, we should not have no errors here. And if we go ahead and again run this with vunit, we can now see that if we take the filter and output from filter, we don't need these anymore. So we can just delete and delete. And now the output from filter, we can see that it's 44252 as it is defined in the implementation. Next thing that we can actually do is we need to add some registers here. So we will first add the filter in, that is an integer, and we need to add it also in this. And what we will now do is we will actually take the request filter and add the filter in here, filter in, and we will put the filter input to it, filter input, and we will modify the get filter output to return filter object dot filter. In. Now as we simulate it, we can actually see that we now get 10,000, so we are looping back from the request filter, that whatever we are requesting we are now returning with the get filter output. Actually we can already, now if we actually go ahead and compile, actually first of all of the packages, and then we go ahead and take this. So if we put in, let's actually make if stimulus counter is larger than 2 to the power of 7, then we will request filter with 44252, and else we will request filter with 0, and if, and at this point if we go ahead and synthesize it, what we should now see, actually we go here and get filter output, we will synthesize this, so get filter output and filter, we will actually stop the previous synthesis here, and as we stop here we can let it run. At this point we actually have our application ready to be then tested with the filtering, because right now we have the application here waits for filter to be ready, and then it transmits the filter output. And once it's done, we should see the square wave from this stimulus here. We have 8-bit stimulus counter as seen in the line 35 over at the top side of this file, and so we have a 50-50 pulse that is 127 clock cycle, 128 clock cycles 0 and 128 clock cycles 44252, and that is going to be the input to our filter that we will be filtering. Now the next thing that we actually need to do is we need to create the aforementioned filter, and when we create design filters in VHDL and use them in FPGA, we most of the time use fixed point filtering or fixed point arithmetic. And what this fixed point arithmetic actually does is that if we just start the PowerShell, is that we in fact do all of the calculations in whole numbers, and it is actually quite intuitive how it works, because if we, for example, multiply 10 by 0.7, now to use whole numbers here we only need to define these so that they are whole numbers. So if we multiply the 0.7, for example, by 100, and then if we use this as the operator for the multiplication, so we multiply 10 by 70, which we get 700, and if we now post divide the result by the same thing that we scaled the original result, we can see that we obviously get the same thing. Now when we do fixed point arithmetic, this is what we do, that we first scale the numbers that we use in the multiplication by some factor up, and then we divide by the same factor afterwards. Now the thing here is that when we use binary numbers, which we do when we use digital logic, if this number is any power of 2, let's say 2 to the power of 16, the division by power of 2 will be just shifting right by the amount to which we raise the power to. So if we, for example, would use 2 to the power of 16, what we would do is, in effect, we would multiply first the 0.7 by 2 to the power of 16, and then we would divide it by 2 to the power of 16. Now this is almost blindingly obvious that it's how it works, because these will just cancel each other out, and the only difference is that the intermediate results are actually used as whole numbers. The way we actually do this thing in VHDL is we can first of all define a function that is actually going to be overloaded multiplication. So if we define overloaded function here, so we overload integer multiplication, which will return an integer. And we're going to use a bit of a trick here, that we will define a variable of signed type. This is going to be called result, and it's going to be signed 36-bit signed value, and we will use this as the intermediate value for catching the multiplication. And the reason we use the signed here is, first of all, this prevents us from continuously or recursively calling the same overloaded integer multiplication. And also in VHDL, integers are 32-bit, and the intermediate value is actually the sum of the bit widths of the inputs to that multiplication. We'll be using 18-bit multiplication because that is what is very common in FPGA hardware. So the way we do this is that we first of all cast the right and left input of the multiplication to 18-bit signed, and we use these signed values, left 18. We will use these to perform the multiplication, and what we will do is we will return the, well, we first of all go back to integer, and we take the result, and we take basically right shifting by the amount we want. Since we are going to be using 16-bit integers, we will be right shifting by 16. Now, since we use bit vectors, this is how we can actually do that. So it identify right and right. Okay, so I typoed, so this should be left. So this is actually a bit shift here. Now, what we'll do is I will actually define a constant radix that is going to be integer and 16, and we will use that here, so it makes it at least a bit more obvious what we are in fact doing. So basically what this does is that here we do the multiplication as I showed with the Python, and this just shifts it right. Basically what we do is we choose a bit slice that is shifted with the amount of radix that we want. Now what we will now do here is we will actually go ahead and return multiplier with 2 to the power of 16, and this should now give us the exact same result as we had before. Since we have overloaded our multiplication. Now if we actually go ahead and put here 2 to the power of 15, the result of our multiplication will be half of it. Right. So next thing that we are actually going to do is we're going to go ahead and create our filter. So what we need is we're going to need first of all a couple of registers that are gonna be called filter out and filter memory. And we need to add them to the initial value, so we will put here 0 and 0. And what we will do then is we're gonna need a few constants. So constant, this is gonna be called filter default filter response constant, which is an integer, and this is gonna be used to define the basically the bandwidth of the filter. So we're gonna use standard names for the filter gains. So constant b0, which is an integer, that is gonna be filter response constant divided by 2, and then we're gonna use b1, which is the same, and then we have a1, which is 1, so 2 to the power of 16 minus filter response constant. If you're not familiar with filtering, doesn't actually matter. We just do some multiplication and summations, basically multiply and add functions here. So next thing that we're gonna do is we're gonna actually alias these, use some aliases for these. So 1, 2, 3, and we're gonna go here, and then alias is filter object dot filter in, filter out, and filter memory. And we have filter here for some reason. So filter. Now the way we're going to use transposed form of a filter, so that means that our filter output or filter out is filter in multiplied by b0 plus filter memory, and then this filter memory is filter in multiplied by b1 plus filter out multiplied by a1. And this is actually our filter here already. We're gonna go ahead and synthesize this. Now, because our application uses the interface functions just by updating, okay, we actually forgot to add it here, so let's put this, so filter out. Right. And stop it. And then let's restart. So while it is synthesizing, what we'll do now is we will actually go ahead and simulate this, and we should see a nice first order filter response from here. 700. Actually we don't, because I am not continuously calling the filter. So let's take this out as well as this, so we call it at every clock cycle. Also we need to compile our header files or packages. And now as we run the script here, and open this, we should see a nice first order filter response. Just add height extension, and then we look at the analog filter here, and voila, we have first order filter response. Now the next thing that I'll show that is if we change this constant here, okay, let's put in here something a bit bigger, so let's put 30. So increase the filter response constant by a factor of 3, we can see that this should now get significantly faster as it does. Also we have unity gain here. I actually don't. Well, that's actually just numerical inaccuracy. Should we round it? We will. Nope, not here, but in here. Now, here's a nice thing. Anyone who is familiar with filtering or fixed point implementation, so we are gonna go ahead and radix -1 down to radix -1. And minus here. So if we now go ahead and run this again, we should now have the filter go up to 10,000. So anyone who is familiar with integer arithmetic, go ahead and explain in the comments why this actually rounds it correctly. Okay, now as we actually get the I wonder if this is ready. It is. It takes 1 minute and 19 seconds to synthesize it. If we actually go ahead and synthesize this into the FPGA, note that this did not actually have the rounding, but as the JTAG has run its course, we can actually go ahead and read the we can launch the uart data receiver, and with this data receiver we can log data. This will run for 300,000 cycles, which means that we have about 3 seconds worth of data here. And then I'll open MATLAB and press read AD, and this one here should show us our first order filter response. Like this. Now if we look at it, the first one is 3276, and then 6752, 9, 12, 14, 17, 19. And if we go ahead and take the, where is it? There it is. This one. Now if we go ahead and look at our waveforms here, actually we changed this response to 30,000. So if we go back to 10, we should see the same numbers in the test here. So first one is we are calling this with 10,000 instead of 44,252. And now look at it. We have 3376, 6752, 96, 12, 13, and then 17, 19, 20, and 26. Right. Now the next thing that we're going to do, that if we look at it, we actually have quite a bit of code just running in the first order filter. But since again we have defined this in a package and records and procedures, we do not need to change the application even if we do change the implementation here. So we can change, for example, the constant, but Also, we can reuse it. Although we're going to do it in the same file, we can actually just create another filter by creating instantiating signal, then calling this create filter again, but with just the filter 2. And we will run these in Cascade by requesting the first filter, and if we go ahead and put the filter is ready filter, and in here we are actually gonna request filter 2, and if we change this to filter 2 and we get the output from filter 2, and we also again run the batch script, so constant interface for filter 1 is missing, so let's put the get filter output filter 1, actually just filter. Now we have actually running, now we have actually managed to do so that with just a few extra lines of code, we have now created another filter with which we are, through which we are actually passing the signals to. And we can now go ahead and put this to be synthesized. Also, actually, what we can do is we can go ahead and take these constants here, and we will actually throw them in the filter record, because this allows us to access them through uart. So we can actually, what we will do now is we will take the filter response constant and take it outside of here, actually in here, and what we will do is we will copy these constants, and we can now, after we create a procedure, we can dynamically actually change the filter response from uart. So the way we do this is, first of all, we add these here like this, so they are initialized as before. If we now run the simulation, this should not change at all. Great. Now next thing that we're going to do is we're going to create a procedure here called procedure called set filter gain, filter response, filter constant, which is going to get the signal filter object. Filter object that is of filter record type. And we will put the filter filter constant, time constant, filter time constant that is an integer. And what we can do here is we can actually again copy these here, this, and then change it so that these are gonna be filter object. What is happening here? Okay, so filter object dot p1, and it's gonna be set to these values over here, and we will actually replace these with filter time constant. E. The filter object cannot be assigned, so we forgot to put here out. And then we need to declare it, so we go here and add it over here. Procedure set filter time constant and 36 GCC. And if we now add this here and test whether or not we messed up anything, so let's say if simulation counter is 5, then we will set filter time constant filter to, let's say, 20,000. As soon as it's just something different, if and if, and then we compile the packages again. And if we run the simulation and look at the waveforms, we see nothing happens. I guess that we are still using these constants here, so we take that out and we use this. So this is filter object B0. This. And here B1 and A1. And we don't need to put here alias, CE alias. So now as we run our test simulation again, now we see that our filter time constant changes here. Now if we go to the LED blinker main and we use the set filter time constant filter and data from uart, and we will actually do this to the filter 2 also. Now once we do this, what we should have then is that we can actually type in some values from uart. We'll actually put that to run over there. And what we're actually programming into the FPGA while it is synthesizing is the previous one where we added 2 of these filters in cascade, so that we get the second order filter response. And we'll be testing that while the FPGA, while the code is compiling. If we look at this here and we put in log and read AD, what we should see here is a second order filter response. It's maybe a bit difficult to see, but as we look at this, we can see that there is this slope in the beginning and slope in the end, which is a characteristic second order response. Basically, we have 2 first order filters in cascade. Now we need to wait for a minute, and while it is compiling, I would like to point out that all of the code, or most of the code, was written here without too many changes to the either the applications. So for the LED blinker main here, where we actually added all of these, all of the code that was synthesized to FPGA, nor even in the actual filter test bench. Now if we look at the filter test bench, which does nothing but runs the filter itself, we can see that it has only a few lines of code. Now if we look at the filter here, we have 132 lines of code here, but I should note that all of this code is actually run here all the time, so it's not very verbose considering that this code is not in either of these 2 files, but it is contained in this one filter package, and it is reused every time pretty much when we instantiate these signals and use these filters. So this is in fact quite efficient use of lines of source code. Now that it has synthesized, we can actually go ahead and start our programmer and run the code into the FPGA. And right now what we should have is a filter that we can change by commanding it through uart or transmitting words with uart. So if we open up this, once we see that the LEDs start blinking now, we can then go ahead and log. And if we get the data, we get 0 because we did not actually. So, yep, we did not actually transmit any numbers here. So if we put in, let's say 10,000 and then log again, now we should see some second order filter responses. There we go. And if we actually put this up, we can see the second order filter response. In fact, if we go even lower, let's put raw 5000. We should start seeing it go towards more and more sine wave as we actually filter out the harmonics of the square wave. So let's put in raw 500. And we look at this one here. We can see it is almost sine. And also, even though we put in 40,000 or 44252, the maximum value is only 22,000 and the minimum is slightly over 21,000. So we actually have almost. By the way, could we in fact go ahead and raw 50E3? Can we actually see the filter response change? We actually can. Magnificent. Yeah, so while we were streaming, we abruptly changed the filter response, which we can see over here. And once we significantly sped up the filter, we can see that it's practically a constant value. And when we speed up the filter significantly, the step response gets much faster. In which case we actually see the original square waveform that we will put into the filter. But both of the rising and falling edges are actually softened up by the filtering, as we can see here. So I think that this is the end of my video. I was running almost an hour already, but what we managed to do in an hour was to create a first filter and then create a test bench for the filter, put the two of those filters in Cascade, and then set the filter response to be configured on the fly from an uart. And if we actually look at the filter or the synthesis results from the FPGA, we should see that we are actually instantiating 6 multipliers, one for each multiplication used here, and we consume slightly under 700 logic elements. This is probably a part 1 of 2 here, and in the second part we will be actually refactoring the filtering here to use only one multiplier, so we'll be using a similar idea that we will refactor the multiplier into its own object, and that will be then used for each of the multiplications. So that will also reuse hardware resources from the FPGA. So I hope this is found somewhat insightful. And if you want to know more and see more extensive examples of this object-oriented style, basically when we hide the functionality inside procedures and records, you can go to hardwaredescriptions.com. I have actually written some blog posts on different types of functionalities that I have been creating so far. So thanks everyone, and bye bye.